The topic being discussed in this tutorial is ionic versus covalent bonding from Module 5. Ionic bonds are defined as the transfer of electrons between a metallic atom and a nonmetallic atom. They form a cation and an anion. They are electrostatic in nature due to the attraction between the oppositely charged ions. There are two possible types of ionic bonds: binary ionic bonds, which involve two monatomic atoms, and ternary ionic bonds, which involve one monatomic atom and one polyatomic atom. Covalent bonds are defined as the sharing of electrons between two nonmetals. When one pair of electrons is shared between two atoms, a single bond is formed and represented by a singular line. When two pairs of electrons are shared between two atoms, a double bond is formed and represented by two lines. Most atoms want to achieve a stable octet, comparable to that of noble gases. The electronegativity between atoms allows us to decide what type of bond will be formed. Electronegativity is a value available on the periodic table that shows an atom's ability to attract electrons in chemical bonds. The greater the difference in electronegativity, the more likely it is for atoms to transfer electrons. Electronegativity is closely related to ionization energy and electron affinity. As you move down a group on the periodic table, the electronegativity tends to decrease. As you move across a period on the periodic table, the electronegativity tends to increase. Most compounds are not completely covalent nor completely ionic, yet they exhibit properties of both depending on the electronegativity difference. To calculate the electronegativity difference, you just need to subtract the electronegativity of one atom from the electronegativity of the other and take the absolute value of that. If the electronegativity difference is less than 0.4, it will result in nonpolar covalent intermolecular forces. If the electronegativity is greater than 2.0, it will result in ionic intermolecular forces. If the electronegativity difference is between 0.4 and 1.6, it will result in polar covalent intermolecular forces. It then gets a little bit more tricky between 1.7 and 2.0. If the electronegativity difference is between 1.7 and 2.0 and only nonmetals are involved, it will be polar covalent. But if it's between 1.7 and 2.0 and a metal and a nonmetal is involved, then it is ionic. To compare properties of ionic and covalent bonds, we must first understand the arrangement of the bonds. In ionic bonds, the compounds are arranged in a giant lattice structure. An ionic lattice occurs because electrostatic forces cause an arrangement where every positive ion has a negative ion adjacent to its position, and every negative ion has a positive ion adjacent to its position. Then, in covalent bonds, there are two positive nuclei that attracts a shared electron pair. This results in a strong bond, but typically not as strong as ionic bonds. Covalent network solids form a crystal lattice structure and become one giant molecule. The specific temperature at which matter undergoes a phase change to go into a liquid or gaseous state is known as the matter's melting and boiling point. Ionic bonds have high melting and boiling points. This is because they require a lot of energy to overcome the electrostatic forces in the lattice structure. Ions with higher charges have stronger forces of attraction. This is evident through the following chart. It is seen that sodium chloride has a melting point of 801 degrees Celsius, whereas magnesium oxide has a melting point of 2,852 degrees Celsius. Then, sodium chloride has a boiling point of 1,413 degrees Celsius, whereas magnesium oxide has a boiling point of 3,600 degrees Celsius. This is a very big difference, even though they're both ionic compounds, and this is dependent on the charges. Covalent bonds have high melting and boiling points. This is because a lot of energy is required to overcome the attractive forces between the polar molecules. The more shared electrons between atoms, the stronger the attractive force and the higher the melting and boiling points. Electrical conductivity occurs when a material can allow charged particles to pass through and transfer a current. A substance can conduct electricity if it contains ions, which are charged particles. So this would lead us to believe that ionic bonds are electrically conductive. Conductivity occurs when electrons are free to move around a material. This means that ionic bonds are not able to conduct electricity if they're in a solid state, but they are able to conduct electricity if the ions are in an aqueous solution or the material has melted to be in liquid form. In contrast to that, covalent bonds do not conduct electricity, with a few exceptions such as graphite. There are no free electrons to move around the material because the valence electrons are being shared between two atoms. They do not conduct electricity in neither the solid nor liquid state. Solubility is a substance's ability to dissolve in a given amount of solvent at specific conditions. Ionic bonds are actually highly soluble in water. Water molecules are polar and therefore have attractive forces that pull the ions in ionic compounds away from one another. The solubility of covalent bonds depend on the substance that it's interacting with. There is a saying that like dissolves like. Therefore, substances of the same polarity are soluble with one another. Compounds of opposing polarity are insoluble with one another. Therefore, polar species are soluble in water, and non-polar species would be soluble in something like oil and fats. Ionic solids have brittle physical properties. This is because when stress is applied to the ionic lattice, the layers within the lattice shift. This causes ions of the same charge to approach one another, causing them to repel. As they repel, the brittle sheets come off and the material breaks into smaller pieces. Then there are covalent bonds, which are very hard because of the strong bonds. They're also very brittle due to the crystal lattice. To initially classify the bond in hydrogen fluoride, it is essential to calculate the electronegativity difference. The electronegativity of hydrogen is 2.20 and that of fluorine is 3.98. Therefore, fluorine is partially negative and hydrogen is partially positive. The electronegativity difference is then 3.98 minus 2.20. The absolute value of that is 1.78. Therefore, it is a polar covalent bond because both elements are nonmetals. Since it is polar covalent, it exhibits similar properties to ionic and covalent bonds because it's between both of them. It actually would exhibit bonds more closely related to ionic since it is so close to 2.0 on the scale. Recall from previous slides that ionic bonds are able to conduct electricity in solution. In solution, hydrogen fluoride becomes hydrofluoric acid. Hydrofluoric acid is a weak acid that only dissociates slightly. Therefore, not that many ions are present for hydrofluoric acid to be a good conductor. It is soluble in water because it's a polar bond and like dissolves like. And since water is a polar bond and the acid is a polar bond, it is definitely soluble. It has a melting point of negative 83.6 degrees Celsius and a boiling point of positive 19.5 degrees Celsius. The next sample calculation revolves around determining the type of bond that is formed in carbon dioxide. I urge you to try this out on your own and then go to the next slide when you want to see the correct solution. Once again, the first step to tackling this problem is to draw out the Lewis dot diagrams for each individual molecule. After drawing them out, take the electronegativity. It is determined that carbon's electronegativity is 2.55 and oxygen's electronegativity is 3.44. The electronegativity difference, as seen on the right, is 2.55 minus 3.44. Take the absolute value of that, which gives the answer of 0.89. Therefore, the intermolecular bonds are polar covalent. But when you draw out the combined Lewis structure, you see that the oxygens are partially negative and the carbon is partially positive. But the geometry of the compound cancels out the partially negatives, and therefore the overall intramolecular bonds are nonpolar. Determine which of the following molecules will dissolve in water: ozone, hydrogen bromide, and methane. Then, state the types of bonds in each of the molecules. I urge you to try this out before you begin and continue on to the solution. Regarding ozone, oxygen has an electronegativity of 3.44. Therefore, the electronegativity difference between each oxygen molecule is zero. When the electronegativity difference is zero, covalent bonds are present within the molecule. When the shape of ozone is drawn out, it is recognized that the center oxygen is partially positive and the other molecules are partially negative, creating a bent shape. The molecule is polar and therefore soluble in water. Regarding hydrogen bromide, hydrogen has an electronegativity of 2.20 and bromine's is 2.96. Therefore, the electronegativity difference is 0.76, resulting in polar covalent bonds. Bromine is partially negative and hydrogen is partially positive, resulting in the molecule being soluble in water. Regarding methane, carbon has an electronegativity of 2.55 and hydrogen has 2.20. The electronegativity difference between each carbon and hydrogen bond is 0.355, resulting in covalent bonds. Although each hydrogen is partially positive and the carbon is partially negative, they all cancel out. Therefore, it is a nonpolar molecule and methane is not soluble in water.